Bismillahirrahmanirrahim. My name is Israr Ali Khan. I am a lecturer at Institute of Numerical Sciences, Cohort University, and here I am going to deliver a lecture on mathematical modeling, MATH-471, and the topic for today's discussion is mixtures. These are the outlines for my today's lecture. Mixture. The mixture of two salt solution of different concentration gives rise to a first order differential equation for the amount of salt contained in it. Mean if we have two mixture in which different amount of salt has already been dissolved, when we mix these two mixtures, or we also call it brine, when we mix these two brine, this always gives rise to the first order differential equation for the amount of salt contained in it. Suppose initially we have a large tank which already has 300 gallons of brine. Suppose another brine solution is pumped into that tank at a rate of 3 gallons per minute. Mean in the tank which already has 300 gallons of solution, another solution is pumping into that tank at a rate of 3 gallons per minute. The concentration of the salt in this inflow is 2 pounds per gallon. It means that every gallon contains 2 pounds of salt. Every gallon that is pumping into the tank contains 2 pounds of salt. When the solution in the tank is well stirred, it is pumped out at the same rate as the entering solution. It means that the rate at which the solution is pumping into that tank is equal to the rate at which the solution is pumping out from the tank. And we know that the solution at which the rate at which the solution is pumping into the tank is 3 gallons per minute. So with the same rate the solution will pump out from the tank. If we denote AT, the amount of salt in the tank at time t, then the rate at which the amount of salt changes we denote by change in A with respect to time, that is equal to input rate of salt minus output rate of salt, mean R in minus R out. The input rate at which the salt enter the tank is the product of inflow concentration of salt and the inflow rate of fluid. We note that Rn is measured in pound per minute, and you can see this is the tank which we discussed in the previous slide. It already has contained 300 gallons of solution. Another solution is pouring into the tank at a rate of 3 gallons per minute, and we said that the amount of inflow and outflow is the same, so a solution is also pumping out from the tank at a rate of 3 gallons per minute. And if we calculate the amount of inflow, that concentration of salt in inflow, that is equal to 2 pounds per gallon. Mean every gallon contains 2 pounds of salt, and the concentration that is pumping into the tank is 3 gallons per minute. Mean with every minute 3 gallons of solution is pumping into that tank, and every gallon contains 2 pounds of salt. When we multiply these two, it becomes 6. It means with every minute 6 pounds of salt is entering into that tank. And now since the solution is being pumped out at the same rate that it is pumped in, the number of gallon of brine in the tank at time t is constant 300 gallon. the inflow rate of the solution, outflow rate of the solution, both are the same. So the amount of the solution will always in the tank will always remain the same, that is 300 gallons. We are not sure about the concentration of salt, how much it would pump out, so we denote it by AT divided by the total amount of that solution. So this is the formula for the R out, AT divided by 300. We are not sure, as I said earlier, we are not sure about how much salt is pouring out per gallon, so we denote by AT divided by 300 multiplied by, and the rate at which the solution is pumping out is 3. When you multiply these two, you would get AT divided by 100 pound per minute. So the rate, the change in the concentration of salt with time is input rate of salt minus output rate of salt. So we know that 6 is the input rate of salt, mean with every minute 6 pound of salt is entering into the system, into the tank, and A divided by 100 pounds of salt is pumping out from that tank. If we bring this A divided by 100 term this side, we can see that it is a linear differential equation in A. Now there are three possibilities for Rn and R out. Either Rn and R out are equal, or Rn is greater than R out, or Rn is less than R out. But here we are assuming that Rn is equal to R out, mean the rate of inflow is equal to the rate of outflow. And this is the first example. A large mixing tank initially holds 300 gallons of brine. Salt was entering and leaving the tank. A brine solution was being pumped into the tank at a rate of 3 gallons per minute. It mixed with the solution there, and then the mixture was pumped out at the same rate. We are discussing the problem numerically now, which we discussed in the introduction section. The concentration of the salt in the inflow or the solution entering was 2 pound per gallon. So salt was entering the tank at a rate 6 pound per minute, mean with every minute the tank, which already contained 300 gallon of solution, 6 pounds of salt is entering into that gallon per minute. And as we know that the solution leaving the system or pumping out the system, the entering and leaving the rate of both of them are the same. So R out is equal to A divided by 300 pound per gallon, and the rate at which the mixture is pumping out is 3 gallon per minute. When you multiply these two, this is equal to A divided by 100 pound per minute. Now here they ask a question: if 50 pounds of salt were dissolved initially in the gallon, how much salt in the tank we were left after 50 minutes. Now you can see this is actually the initial condition. If 50 pound of salt were dissolved initially in 300 gallon, mean initially in the gallon we have 50 pounds of salt. I'm going to summarize the problem again. A large tank that contains 300 gallon of solution in which 50 pounds of salt has already been dissolved, and the inflow rate of the solution and outflow rate of the solution both are the same, that is 3 gallon per minute. All we have to do is to find how much salt is left after 50 minutes. And as we know that the rate at which the amount of salt changes, that is equal to dA divided by dt equal to R in minus R out. And you can see this is the initial dA divided by dt, 2 the amount of salt per gallon, and 3 is the rate of inflow of the mixture, and minus A divided by 100. And you can see this is the initial condition. A of 0 is equal to 50, mean initially 50 pound of salt is dissolved in the system. And you can see this becomes a linear differential equation in A, and we know how to solve a linear differential equation. We find the integrating factor e raised to power 1 divided by 100 dt. This become e raised to power t divided by 100. We multiply this integrating factor both sides to equation number 1, and then it becomes this d divided by dt e raised to power t divided by 100 multiplied by a, and this thing. If we use product rule of differentiation, we can easily get this previous step. Then we multiply dt both sides, and it becomes this. We apply integration on both sides, and this becomes e raised to power t divided by 100 is, and e raised to power t divided by 100 multiplied by 600 plus c, a constant of integration. We divide both sides by e raised to the power t divided by 100, so it becomes equation number 2. And now this is the general solution, and now we are going to apply the initial condition. When t is equal to 0, the amount of salt is 50. This equation number 2, we put t 0 and a is equal to 50 to find the value of the arbitrary constant c, and this c then comes out is minus 550. We put this value of c in equation number 2, and we get this. A is equal to 600 minus 550 multiplied by e raised to the power minus t divided by 100. And equation number 3, you can see that now here we are left with only 2 variables: a, the amount of salt, and t, the time. If either one is given, we can easily find the other one. In this question, we are given with the time. When t is equal to 50, we have to find how much salt is left in the system. When we put t is equal to 50 here, we get a is equal to 266.41 pound. So this is the amount of salt we are left after 50 minutes. If you look at equation 3, in the right side of equation 3, we can see there are 2 terms. This one with no t we called the steady state term, and this one with t we called the transient term. With the passage of time, when this term reduces, and it eventually become 0 for a large amount of time, and so a would become 600 pound. We can write this in mathematically. When a approaches to 600, a approaches to as t approaches to infinity. Now this is another problem 21, exercise 3.1. A tank contains 200 liters of fluid in which 300 grams of salt is dissolved. Brine containing 1 gram of salt per liter is then pumped out the tank at a rate of 4 liter per minute. Mean a solution is pumping into the tank at a rate 4 liter per minute and every liter contain 1 gram of salt. Then well mixed solution is pumped out at the same rate. Mean the rate of inflow and outflow is the same. Find the number AT of grams of salt in the tank at time t. We have to find the amount of salt after in the tank after time t. Now this is a solution. We know that the rate at which the amount of salt change, that is equal to R in minus R out, and 1 is the amount of salt per liter and 4 is the rate at which the salt is pumping into that mixture. And we know that the rate at which the salt is leaving the system, that is equal to A divided by 50. And we are given that initially 30 grams of salt is dissolved in the mixture. Mean when time t is equal to 0, the amount of salt is 30. So when we bring this term to this side, we can clearly see that this is a linear differential equation. We know how to tackle a linear differential equation. We first find the integrating factor, which is e raised to the power t divided by 50. Then multiply this integrating factor with equation 1. And it becomes this, and we know how to come to this side, and when we apply the product rule, we can easily get to this previous step. And then we apply integration both sides, and we get this thing with an arbitrary constant c. We divide both sides by e raised to the power t by 50, and we get this thing. And now to find the value of arbitrary constant c, we apply the initial condition. We put t is equal to 0 and a is equal to 30 to get the value of the arbitrary constant c. And when we put these two in equation number 2, we get c is equal to minus 170. And now this is our general solution. A is equal to 200 minus 170 multiplied by e raised to the power minus t divided by 50. And in this solution, we again can see that the right hand side contains two terms. The one is steady state term, which contains no t and this one is the transient term, which depends on t. When t is very large, then a would become 200. After a very long time, the amount of salt in that mixture will be 200 grams. And now this is the third problem, number 22, exercise 3.1. Solve problem 21, assuming that pure water is pumped into the tank. Now instead of a solution pumping into a tank, pure water is pumping into this tank. So the amount of salt, the change in amount of salt with respect to time, that is equal to R in minus R out. And you can see there is 0. It's 0 is because no salt is entering into the system. Water is pumping into the system, but that is pure water. So 0 minus, and the amount of salt that the system already has, that is equal to minus a divided by 50. And you can see that this is a separable equation, and the solution of which will give us a is equal to c e raised to the power minus t divided by 50. Now to find the value of this arbitrary constant c, we put t is equal to 0 and a is equal to 30. When we put these two, we get c is equal to 30, and equation 2 becomes this: a is equal to 30 multiplied by e raised to the power minus t divided by 50. And you can see that this solution contains only transient term. There is no steady state term. Means with the passage of time, when t is very large, all the salt that is in the tank will pumped out from the tank, and the amount of salt in the tank will be 0 for a large t. When t approaches to infinity, a will definitely approach to 0. Now this is the reference. Thank you very much.